Q into mu P. These are the conductivity equation for n-type and p-type semiconductor. Now we will see the temperature coefficient for n-type and p-type semiconductor. Let's take an example of n-type and p-type semiconductor. First, in intrinsic semiconductor, for example, n equal to p equal to 10 raised to power 10. Then according to mass action law, n into p equal to 10 raised to power 10 into 10 raised to power 10 equal to 10 raised to power 10 into 10 raised to power 10 equal to 10 raised to power 20. And if we add the total number of charge carrier in intrinsic semiconductor, then n plus p equal to 10 raised to power 10 plus 10 raised to power 10 equal to 2 into 10 raised to power 10. In case of n-type semiconductor, for example, I take n equal to 10 raised to power 15 and n equal to 10 raised to power 5, then n into p equal to 10 raised to power 15 into 10 raised to power 5 equal to 10 raised to power 20. According to mass action law, both the values are same. We have changed the composition, but we have kept the material at thermal equilibrium, and according to mass action law, the product of hole electron and hole concentration is same in both the cases. Now if we add the total number of charge carriers, then n plus p equal to 10 raised to power 15 plus 10 raised to power 5 is nearly equal to 10 raised to power 15, which is very greater than 10 raised to power 15 is very greater than 10 raised to power 10, as this much difference is there in the total charge carrier concentration in extrinsic semiconductor and intrinsic semiconductor. So I can conclude that the total number of charge carriers in extrinsic semiconductor n-type or p-type is far greater than the total number of charge carriers in intrinsic semiconductor. So with increase in temperature, more number of charge carriers will be generated, and uh, already we have seen that the charge carrier concentration is very large in extrinsic semiconductor. So I can say that with this much concentration of majority charge carriers in extrinsic semiconductor, it is become very difficult for majority carriers to move in the material and mobility is badly affected by the temperature. Hence finally we can conclude that in n-type or p-type material, conductivity decreases with temperature. That is, conductivity of n-type and p-type has negative coefficient of temperature. Now we will define resistivity of the material. Resistivity, written as rho, is the reciprocal of conductivity. Means resistivity is the reciprocal of conductivity. If we know the equation for conductivity for all the materials, then we can also calculate its resistivity. First, for intrinsic semiconductor, For intrinsic semiconductor, sigma equal to Ni into Q into mu n plus mu p. So its resistivity will be defined as rho equal to 1 upon Ni into Q into mu n plus mu p. Conductivity of intrinsic semiconductor increases with temperature. Temperature increases, conductivity increases. If conductivity of intrinsic semiconductor increases, then resistivity decreases with temperature. Means resistivity of intrinsic semiconductor has negative coefficient of temperature. Number 2, N-type semiconductor. For N-type semiconductor, conductivity is defined as sigma is equal to Nd into Q into mu n. If conductivity equal to Nd into Q into mu n, then the resistivity will be equal to 1 upon Nd into Q into mu n. For N-type semiconductor with increase in temperature, conductivity decreases, then resistivity increases. Means resistivity of N-type semiconductor has positive coefficient of temperature. Number 3, P-type semiconductor. In case of P-type semiconductor, conductivity is defined as sigma equal to Na into Q into mu p. If conductivity is equal to Na into Q into mu p, then resistivity will be reciprocal of this 1 upon Na into Q into mu p. With increase in temperature, conductivity of P-type semiconductor decreases, hence resistivity increases. Now, resistance of the material. Resistance. A resistance is defined as R equal to rho L by A. For example, this is the material for which we are calculating resistance. For this material, its cross-sectional area will be A. This is cross-sectional area, and this will be the length of material L, and this rho will be resistivity of the material. We know the equation of resistivity for intrinsic n-type and p-type semiconductor. So calculating the resistance for different type of material will not be much difficult if we know the equation for resistivity. Also, the uh, unit for resistance is ohms. If the unit for resistance is ohms, so I can write from here resistivity rho equal to R into A by L. Means ohm into meter square by meter equal to ohm meter. From here I can define the unit of resistivity equal to ohm meter or ohm centimeter. Next, conductance. Conductance of the material is written as G, and it is the reciprocal of resistance of the material. The unit for resistance is ohms, so then unit for conductance will be ohms or Siemens. Yes. We know that R equal to rho L by A. From this equation Uh, G can be written as 1 upon rho L by A. It can be written as A into sigma divided by L, where 1 by rho equal to sigma conductivity and unit is Siemens or mho. This is the conductance of the material. If we know conductivity of a material, then we can calculate its conductance. Now we will solve a problem on related to conductivity conductance. Given data is all electron mobility ratio equal to 0.4, doping concentration equal to 4.2 into 10 raised to power 8, sorry, into 10 raised to power 8 atoms per meter cube. Intrinsic concentration equal to 1.5 into 10 raised to power 4 atoms per meter cube. Calculate the ratio of conductance of n-type semiconductor to the conductance of intrinsic semiconductor. The material is material is n-type semiconductor. It is given in the problem. This question was asked in GATE 2006 electronics paper. We know that conductance of a material is equal to 1 by resistance, and resistance equal to rho L by and resistance R equal to rho L by A. From this equation we can write as conductance equal to sigma A to A divided by L. Now for n-type semiconductor, conductivity is defined as sigma n equal to Nd into Q into mu n, and for intrinsic semiconductor, conductivity is defined as sigma I equal to Ni into Q into mu n plus mu p. Putting the corresponding values, we can calculate the conductivity for n-type and p-type semiconductor, n-type and intrinsic semiconductor. But in the given problem, conductivity is not given directly, but a ratio of electron to hole mobility mu p upon mu n is equal to 0.4 is given. Now the ratio can be found out as Gn upon Gi is equal to Nd into Q into mu n upon Na into sorry upon Ni into Q into mu n plus mu p. Q cancels out and value of Nd is given as 4.2 into 10 raised to power 8 divided by Ni is given as 1.5 into 10 raised to power 4, and mu n and mu p are not given, so we can write this as 1 upon mu n plus mu p divided by mu n divided by mu n. So we can write it as 4.2 into 10 raised to power 8 divided by 1.5 into 10 raised to power 4 into 1 upon 1 plus 0.4. Solving this, we get Gn upon Gi equal to 20,000, which was in option. Gn upon Gi equal to 20,000. Now we will study about drift and diffusion mechanism. Drift mechanism. Suppose there is a material. In this material, if we apply a battery across it, we then due to application of this supply, an electric field will act on this charge carriers, and due to this electric field, holes move in the direction of electric field and electrons will move in the opposite direction of electric field. This motion of charge carriers due to applied electric field is called drift motion. So I can define drift mechanism as motion of charge carriers under the effect of applied 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 electric field under the effect of applied electric field is called drift motion, and the velocity of charge carriers due to drift motion is defined as Vd, drift velocity. Means we can now say that drift motion is possible only if we have an electric field applied across the material. Another mechanism of charge carrier motion is diffusion. Suppose we have a material. In this material, we are looking at this cross section, and to the left hand side of this cross section, this is the charge carrier concentration. Here, for example, I have taken electrons, and to the right hand side of this cross section, this is the charge carrier concentration. By observation, it can be clearly seen that the electron concentration on this side is far greater than the electron concentration on this side. If we move with a very small distance dx from this point to this point, there is change in electron concentration dn. Means in this material at this cross section point, there exists a change in electron concentration with respect to change in distance, and this ratio is called concentration gradient. It is called concentration gradient. If in a material there exists a concentration gradient, then the charge carriers have tendency to move from higher concentration to lower concentration, and this motion of charge carriers from higher concentration to lower concentration is nothing but diffusion of charge carriers. As the charge carriers move forward, diffusion starts decreasing, and i I can say that diffusion will die out where the concentration of electron in the material will be uniform. From this point diffusion starts, and at this point the diffusion ends. This is called L, diffusion length. Here many charge carriers come forward, and after some time the concentration will be little bit higher here, and now the difference in the carrier concentration at this point will be less as compared to this difference dn with this dx. So the diffusion uh, continuously decreases, and one point when the total concentration of electron in the material becomes uniform, at this point the diffusion will die out, and this starting point to end point, this length is called diffusion length, and this diffusion length is defined as L equal to under root of d into tau, where d is called diffusion constant and tau is called minority carrier lifetime. So in drift mechanism, due to application of electric field, charge carriers move, while in diffusion without an electric field, charge carriers move from higher concentration to lower concentration.